Hello everyone, this is Chakradhar and this is the walkthrough video of the project uh, in the Neural Networks and Deep Learning course. And this project is about building a LSTM model to forecast the temperatures based on the previous 24 hours climatic conditions. Um, yeah. After importing the required packages, I have loaded the data sets. And initially the datetime is not the time series object, so I have converted the datetime attribute into time series object, and I have set it as an index. Uh, so the next part is the exploited data analysis, and here we can see that the total of 52566 instances and 14 attributes, and the first 5 instances are displayed here. And here we can see that all of the attributes are the numerical, because every attributes are describing the climatic condition for of the temperature, like the humidity, air temperature, H2O content. So all of the after all the matrix will be numerical. So that's why all of the attributes are having the numerical attributes. And after that, we have checked for the missing values, and fortunately, we don't have any missing values. So the data set is in a very good shape to do any further analysis. Yes. When it comes to the statistical description of the data, here we described everything. So this helps us to get an overview, like how the attributes have, how the attributes are having the are distributed. Like if you see the RH, the minimum value is 13 and the max value is 100. So the 50th percentile is at 79. So that means it is close to maximum. So we can say like mm, and the dataset having a right skew distribution. So when we see the correlation of all attributes with others, we can see that there's a high, most of the attributes are having the high correlation with the others. So we can say that there is a multi-collinearity in the data. Usually if we have the multi-collinearity, the models will be overfitted to the training data. So we have to take some measures to rectify that. And this is a pair plot, and all of the diagonal things will show the distribution of the attribute, and the rest will show the scatter plot between the attributes. And here we can see that some of the attributes are having correlation of 1. And after that, I am showing the time series characteristics of the data. And here I have calculated the mean temperature for every month over all years. So that's why that's how it is plotted. And here we can see the data, the distribution is a bell curve, and here we can see the temperature will be low at January and February and will be high at 6 and 7. Again it will be low at December. And this is the original distribution of the data, and again I have plotted it here. Here we can see the original distribution of the data, and it's like, and also here we can see the overall trend in the data. So there is a slight increase in the overall, slight increasing trend. Maybe it's because of some global warming and those kind of issues, which is irrelevant to us. And here also we can see the seasonality in the data. So because of the slight increasing trend, there is no constant mean and variance. So there is no constant mean. So the data is not stationary. After that, I have performed the latent factor analysis to determine the latent factors. So I performed the Bartlett test. We got p-value 0.0, indicating that the data is statistically significant, and also the KMO value we got 0.7, which should be greater than 0.5. So all of this is showing that the data is well suited to do factor analysis. And when I did the when I did the factor analysis for all the components, here all the covariance values I got. So after 5 factors, it's the remaining factors are not having some good covariance values, so it's good to go with 5 factors. And here also we can see that. So all of the loadings are the correlation between the factors and the original attributes. And so the components which are having the high correlation with the factors are the driving components, and that's why here we can see the T pod, TD, VP max, V packed and H2OC are having high correlation with the factor 0. So these are the driving components, and this will indicate that all of these attributes are having the some shade covariance, and that's why I need the factor analysis to find that. And for I did the pre-processing like normalization for the neural network, because we have to normalize the attributes to perform for any model building, and that's the basic step. And I'm not doing the normalization for the y attribute, because when I did the normalization the results were not that good, so I did that. And I had that. After that I split the data to get the validation data set to track the model performance, and I have that. I have reshaped to to get an keras acceptable form. And when it comes to the model building, this is my best model for which I got the best results. And this is how I have implemented with 4 LSTM layers, and each having 128, 120, and 64, 128 nodes. And after the first layer, I have performed that. I have implemented the dropout layer to reduce some overfitting. And after I perform, the loss, I have used the mean squared error as a loss function to magnify the error rate. So that's how it will be decreased. And also the metrics as MAE, and I have used the batch as 150, and I have trained it for 50 epochs. After that we can see the mean error 0.5162 and the validation error is 4894, indicating there is no overfitting of the data. And these are the error rates and the loss function plots for the validation on the validation and training data sets. After that I have I got the predictions on the test data set, and when I submitted to Kaggle I got the mean absolute error as 0.50204, and which is a very good result. And my ranking is 2 in the data set and in the computation. And when I did the private ranking, when it got updated, my private ranking is 3. Thank you.